So our next speaker is Dave Swinarski, and his title is The Mukai Model of M7.
Thanks so much, Chuck. First of all, to everybody who's joining the meeting right now, I hope that you and your loved ones are safe during the pandemic. And second, I'd like to give a warm thank you to the organizers for inviting me to speak today. Over the last 2 years, I've been serving as an associate dean at my university, and it's been a wonderful opportunity, but there's very little time left for research. So when Vanya emailed me and asked me to be a part of this, I decided that I was going to dust off an old project and try to do some new calculations, and that's what I'm going to tell you about today. So thank you for inviting me back into algebraic geometry, Vanya. Let's see, oops. This is joint work with Patricio Gallardo, Jesus Martinez Garcia, and Hanban Moon, and it all started as part of an AIM Square that we organized on computational aspects of GIT with a view of moduli spaces. Just so I am honest about how far I got in preparing this talk, I'm going to describe calculations today that prove something new about two examples. One is the Fricke-MacBeth curve, which is a certain curve of genus 7 with lots of automorphisms. And the second example I'll discuss is a genus 7 curve with 7 cusps that has a dihedral symmetry. And the result is that these are both T semi-stable in Mukai's model for a certain maximal torus in SO10. And of course, the experts in the room know that I really, really want to replace this T with a G instead, but I haven't been able to do that yet. So here's an outline of my talk. First, I'll describe Mukai's construction of his model of M7. I'll spend some time talking about background on geometric invariant theory, GIT. Then I'll present 3 examples and 3 different strategies that I'm using to work with them. And then in the last few slides, I'll describe some of our ideas for future work to extend the results that we currently have. So it's the beginning of the academic year in many places. And so in case there are new graduate students among us, I'll start from the very beginning. MG is my symbol for the moduli space of smooth curves of genus G, modulo isomorphism. And of course, it's not just a set, it actually has the structure of a quasi-projective singular variety of dimension 3G minus 3. If you only look at smooth curves up to isomorphism, you don't get a compact moduli space, but there's a very famous compactification due to Deligne and Mumford. We need to let in some singular curves, but we let in the mildest ones possible. And so the boundary of this compactification consists of curves that have only nodes as their singularities. And we further insist that it needs to have a finite automorphism group. And there are many open problems about these beautiful spaces. One is to understand its birational geometry. And today, I'll do that, and the approach I'll take is by constructing different compactifications of it. So there's a lot of different strategies that people have used to probe the study of the birational geometry of MG bar. People have run the log minimal model program with great success that generally goes by the name of the Kiel-Hassett program. There's other people who look for modular compactifications of MG, and there are lots of interesting results in that direction. Today, I'm going to start with one well-known construction of the moduli space and start tinkering with it. And that is, I guess, another approach that we can take. So let me start with Gieseker's construction of MG bar as a GIT quotient. So let's let C be a smooth curve of genus G greater than or equal to 3. Let's fix a positive integer mu greater than or equal to 2, and you can consider the embedding in given by multiples of the canonical divisor. Then we can compute the degree of this divisor, so it'll be nu times 2g minus 2. And we know the associated Hilbert polynomial for an object with that degree and genus. And we can also compute the dimension of the space it would embed into. And so any curve embedded by a system like this should appear in this Hilbert scheme. And of course, since you can make a choice of basis of this linear system, it'll actually be represented by an entire PGL n+1 orbit in this Hilbert scheme. And Giesecke's idea was as follows. Within this Hilbert scheme, find the locus of things that are truly embedded by that linear system. And if you take a quotient by a PGL n+1 or its finite cover SL n+1, then at least set theoretically, you would expect to get MG. And Giesecker made all of that work. And in fact, he showed that if you take nu greater than or equal to 5, and if you embed your Hilbert scheme in the right Grassmannian, which I'll explain in a second, you not only get MG, you can actually take the closure of this locus J and you get MG bar. I got slightly ahead of myself on my slide. We can naturally embed the Hilbert scheme into Grassmannians of different sizes. And here's the map that does that. Take any subvariety of Pn and map it to the nth degree slice of its ideal thought of as a subspace of degree m polynomials. And when m is large enough, and it really needs to be asymptotically large for this to work, you get an embedding of the Hilbert scheme into a Grassmannian of very high dimension. At the other end of the spectrum, what happens if you set all of these parameters to their lowest values that still make sense? Okay, so when genus G equals 7, I suppose I could break this rule and I could even let nu equal 1, and m is the smallest, and m equals 2 is the smallest integer that makes sense to me. Even if you set all those values that low, which is much lower than Giesecker would want you to, you're still working in a Grassmannian of 10-dimensional subspaces of a 28-dimensional space. Okay, and I'm only doing this calculation so that you can see in the following slides that Mukai is able to work in a much smaller parameter space. Okay, so that was Giesecker's approach, which I'm taking as sort of the theme. And now what's Mukai's approach, which is really quite different? Well, let's start with the observation that the canonical ideal of a curve of genus G greater than or equal to 3 in general is generated by quadrics, by Petri's theorem. And specifically, if you're working in genus 7, you need 10 quadrics in P6. Mukai observed that for a general smooth genus 7 curve, and here by general I mean it should be not hyperelliptic, not trigonal, and not tetragonal. If you look at the multiplication map from sim2 of the degree 2 part of the canonical ideal into the degree 4 part of the canonical ideal, this has a one-dimensional kernel. And so we can choose a generator Q of that kernel, and we can think of it as a quadratic form on the vector space of quadrics. Now, whenever you have a quadratic vector space, the question you want to ask yourself is, what are the isotropic subspaces? And Mukai further observed that if you look at the row space of the Jacobian matrix evaluated at any point on your curve, this matrix, since we're working on a non-singular curve in P6, is going to have rank 5. And it's also easy to show that it's isotropic for the form Q just by taking some partial derivatives of Q evaluated on your quadrics. And so we get Lagrangians of this quadratic vector space. And the assignment of this Lagrangian to this point P, Mukai denotes WP per. And so here's a quick summary of Mukai's results from his 1995 paper. When C is general, in the sense I described on the previous slide, if you look at the map that takes the point P to the Lagrangian subspace WP perp, that gives an embedding of C into the orthogonal Grassmannian of 5-dimensional isotropic spaces of a 10-dimensional quadratic space. The orthogonal Grassmannian, in turn, embeds via the spin representation into P15. And this map is an embedding of C. Furthermore, you can recover C as the intersection with a 6-dimensional linear subspace of P15. And when you do, in that linear subspace, C is canonically embedded. And finally, okay, so your 6-dimensional linear subspace P in P15 is cut out by 9 hyperplanes. And so if you look at the Grassmannian of 9-dimensional subspaces of a 16-dimensional vector space, and look specifically at the set that intersects the orthogonal Grassmannian transversely, you should be able to recover all of these linear spaces that way. And Mukai shows with a dimension count that indeed, if you take the quotient of this open sets by SO10, which preserves the quadratic form Q, that you get something of dimension 3G minus 3, and you have a model of M-SEM. And so in the rest of the talk, I want to talk a little bit more about this quotient and how we can study it and what compactification of M7 we get from this construction. So in algebraic geometry, there are several different ways of forming quotients by a group action. It's much more difficult than it is in the topological or in the differential geometric categories. One way to form a quotient of a scheme by an algebraic group is called geometric invariant theory. And this goes back to Mumford in the 1960s. And in GIT, we actually start off with 2 ingredients. There's, of course, the space X that has a group action, but we also give ourselves a linearization of the group action, which is a lifting of the group action to a line bundle. Then you can define the GIT quotient scheme as a proj of the ring of invariant sections of this line bundle. Now, things are a little more delicate than they are in the topological or differential geometry categories because in general, you would expect that whenever you form something called a quotient, that the quotient map would be a morphism in that category. And that's not exactly true in GIT. What you're always guaranteed is that there's a rational map from your parameter space to this quotient. But what could go wrong? Well, if you have a point in your parameter space where all the G invariant sections vanish, that's where this map would be undefined. And so we make a definition. The points where there's a non-vanishing invariant section are called GIT semi-stable. And those are the points where the quotient map is actually a morphism. The opposite of semi-stable is called unstable. And there's also a notion of stability, which is semi-stability plus having a closed orbit. But I'll mostly just talk about semi-stability in this talk. Okay, and so when somebody gives you a group action in algebraic geometry, if you're doing GIT, what you look for is a linearization, and then your goal is to describe the semi-stable locus so that you know when this map is actually a morphism. So one tool we have to help us in this analysis is the Hilbert-Mumford numerical criterion. And part of it says that you can test GIT semi-stability by working one parameter subgroup at a time. Now, in the next few slides, I'm gonna focus on semi-stability with respect to a maximal torus, T inside G. In many applications to moduli problems, what we actually care about is the quotient by the group G, not a maximal torus T, although there are some interesting cases where you're quotienting by a maximal torus too. And I just want to point out in advance that the reason I'm going in this direction is that it's sometimes possible to first compute T semi-stability and then extend that to G semi-stability. So that really is my goal. And for me, this is going to be a step along the way. All right, so for a few slides, let's just focus on a torus T acting on a finite dimensional representation, W, and let's let S be the set of weights of T on W. Now, our torus is abelian, and so you get a decomposition of your representation into weight spaces indexed by the weights in S. And now I'm going to give you a little bit more detail in the Hilbert-Mumford numerical criterion. So it's still true that stability, you can test one parameter subgroup at a time. And now, if you're working with a one parameter subgroup lambda, what are you looking for? You're looking for there to be at least one character in S, so that lambda pairs negatively with that character, and your vector has a non-zero coordinate in that eigenspace. Okay, so just stop and think about this for a second. If you have one parameter subgroup action and the weights are all positive, then as you let T go to 0, your vector goes toward the 0 vector. And if we're supposed to stay in projective space, that's bad. And so that's why we want at least one negative exponent in a place where there's a non-zero coordinate. And we can actually picture this. So a few more definitions. A state is just going to be a subset of the set of weights. And the state of a vector is going to be the set of weights where a given vector has non-zero coordinates. And now we can give a really nice picture of T semi-stability or stability. And so here, my diagrams correspond to what you would get if you look at the representation corresponding to a pencil of 2 quadrics in P2. So it's a fairly wimpy example, but I think we can still get the point across. Within each of these diagrams, I've drawn a point that would correspond to the trivial character, which is not actually in this particular representation, but if you subdivide your lattice, you can see where it would be. And now I want you to imagine drawing hyperplanes through the trivial character in these pictures. And then your one parameter subgroup would be a vector orthogonal to any such hyperplane. When you draw that hyperplane, if all the weights are positive with respect to lambda, that means all the points would be on one side of your hyperplane. And so actually, I guess I'm describing instability or non-semi-stable. Okay, so here's an example where all of the non-zero coordinates lie on one side of a hyperplane. And so we can see here's an arrow lambda for which we would have instability. In contrast, over in this picture, any hyperplane you draw through the origin has weights that are on both sides. And so that corresponds to stability. And so when we're working with a torus, we get this really nice picture of semi-stability in terms of these states and whether they contain the trivial character or not. I want to push this picture one step further and describe an object that appears in the literature many, many times, and as far as I know, has no official name. I like to call it the instability fan, and I'm certainly not the first researcher to consider it, but I may be the first person to use this particular name for it. Okay, so first a couple of definitions. For any one parameter subgroup lambda, we can form a state associated to lambda. It's just going to be made up of all the characters that pair non-negatively with our one parameter subgroup lambda. In the other direction, if you're given any state, you can form a cone, and it's given by all the lambdas that pair non-negatively for everything in your states and non-positively for everything outside your state. It's clear from the definition, we have a finite number of elements in the set S. So these are closed finitely generated polyhedral cones. And with a little more checking, you can check that as lambda varies, the cones of the states of lambda vary nicely too, and they form a fan. And I call that the instability fan. And just to give an example, here's a portion of the fan if we're working with pencils of plane quadratics. By Weyl group symmetry, I don't need to show the entire two-dimensional plane. I can just show this sector of it. And you can see within this cone, sorry, the gray here just indicates where my fundamental domain for the Weyl group picks up and leaves off. Any one parameter subgroup, so an arrow landing in this sector, you can draw its orthogonal hyperplane, and you can select all the weights that are on the positive side. And so all of the arrows in this cone give you this set of those dots that are shaded black. And then as you cross this wall, you can see there's one dot that's on the hyperplane. And as we reach the next cone, now that dot is now on the negative side of that hyperplane. And so we get a slightly different state in this cone compared to that cone. And it's easy to see that as you cross walls, you know exactly which weights in S are going from negative to positive or vice versa. And so it's easy to track what happens as you cross walls to go from one cone in this fan to a neighbor. And so that allows us to easily describe two different algorithms for computing this instability fan. The first one is a simple breadth-first search. Start with a random one parameter subgroup and find the cone around it. So let's say you had a one parameter subgroup that landed in this cone. You'd compute the state, and then you'd compute the cone associated to that state. And now you want to cross each facet of that cone. As you do, you can track what happens to the state. You can use your new states to build new cones. And now you just want to search for all the neighbors of every cone that you find until you've crossed every facet in every direction. And you know that you found them all. That algorithm works, by the way, and I've written a fairly simple Macaulay 2 package that implements this. But you can imagine that for complicated examples, when there's lots and lots of cones, this is a fairly time-consuming thing to do because you're doing lots and lots of convex geometry calculations to find facets of cones. So what many researchers, including me and my collaborators, have done is to use variants of a simpler algorithm. Now, this one doesn't give me the entire fan, but it'll at least help me compute the rays. And we simply say, all right, well, every ray in this fan, let's say the rank of the torus is R, has to lie on R-1 linearly independent hyperplanes. So just test each subset of the right size and figure out which ones are linearly independent. And if you find one, compute the complementary ray. That's in some cases much faster than algorithm 1. It allows us to do examples where there are possibly many cones. And in particular, we got this to work for the GFT problem behind Mukai's model. So with Patricio Gallardo and Jesus Martinez Garcia and Haban Moon, we were able to compute the rays in instability fan. And we only worked up to symmetry by the Weil group, and we found almost 5 million rays. So this instability fan is a highly complicated one. Doing algorithm 1 seems unlikely to work. And like I said, we have an enormous number of rays, and that's even up to symmetry. And what I just described was all about T semi-stability. And as we know in Mukai's model, what we really want to describe is G stability. And so I just want to briefly mention 2 techniques that have been used to pass from T semi-stability to G semi-stability. The first approach is very geometric. And so what you do is you identify all the maximal non-semi-stable states, and then you look for a coordinate-free geometric interpretation of what kind of object could produce that maximal non-semi-stable state. And I'm not going to go into this in too much detail here, but I'll simply say there's a cute section in Harrison Morrison's book, Moduli of Curves, where they work this out for the plane cubic. You imagine that you've got a hyperplane of degree 3 and peak 2, and you start imagining that more and more of the coefficients are 0. So your state is getting smaller and smaller. Suddenly it's unstable, and they conclude that if your curve only had nodes as singularities, you wouldn't have gotten that maximal unstable state. And so the conclusion is that GIT semi-stability for that GIT problem corresponds to only nodes as singularities. But that particular description is coordinate free. And so now you've managed to pass from T to G. Well, for Mukai's problem, first of all, we're working with 9 hyperplanes in P15. So that seems like it's going to be much trickier than the plane cubic example. And on top of that, there's 5 million rays in the instability fan. And although I haven't computed how many maximal non-stable states there are, there's potentially lots. So we're looking for another way to pass from T semi-stability to G semi-stability. And I want to discuss some results that are due to Kempf, or at least inspired by Kempf, for doing that. So Kempf proved that when a point is unstable in GIT, there's a worst 1-parameter subgroup lambda. That's a bit of a misnomer. It's not actually unique, but you can show that there's a numerical function and that lambda maximizes that function, and it's worst in that sense. Moreover, associated to worst destabilizing lambda is a proper parabolic subgroup P lambda, and it's given by all the elements for which this limit exists. Kempf shows that every maximal torus in your parabolic contains exactly one worst one parameter subgroup. And he also shows that this parabolic contains the stabilizer of X. Okay, and that is the part that we're going to try to mine. So already in his paper, Kempf recognized a corollary. If your stabilizer isn't contained in any proper parabolic, then X can't be unstable. So it must be semi-stable. Now, a variation on this was proposed by Ian Morrison and I, and we worked out some cases where the group G was SLN. And roughly speaking, I'll phrase our idea this way. You want to describe the parabolics that might contain your, that contain your stabilizer, and then compute T semi-stability for maximal torus in each one of them. And if you're lucky, there won't be too many parabolics and too many maximal tori to test. And once you do the calculations associated to them, you're done. So we managed to work that out, like I said, when G is SLN. And probably the most spectacular application was actually due to Alper, Fedorchik, and Smythe, who used that to study finite M stability of Hilbert schemes modifying Giesker's construction of MG bar. Okay, so let's say we were going to try to do that in the GIT problem for Mukai's model. I'm looking for objects that have stabilizers, so let's take a look at genus 7 curves with automorphism groups. The bigger, the better. Well, it turns out that algebraists have classified all of the finite groups that can be automorphism groups of curves of genus G for the genus going up to about 100. Breuer and Konder produce massive lists where they give you not only the automorphism groups, but all of the subgroups of those automorphism groups. Maegard, Shasta, Spektorov, and Folkling give you a more refined list. They only go up to genus 10, but they'll tell you what the full automorphism groups of your curves are. And I think both lists are working in the case where we assume that the automorphism group is large relative to the genus. And here large means greater than 4 times G minus 1. A few years ago in a paper, I actually found equations of all the curves on Maegard, Shasta, Spektorov, and Folkling's list going up to genus 7. So let's take a look at what we've got in genus 7. So there's 13 isolated curves with large automorphism groups. And the first 2 columns in both halves of this table come from Maegard, Shasta, Spektorov, and Folkling. After I got equations, I was able to compute the Betti tables of those ideals, and so I actually know the gonality of those curves. And what you can see is that almost all of these are trigonal, hyperelliptic, or tetragonal. There's only 3 that are general. There's this curve, which has the largest automorphism group in genus 7. And then there's 2 conjugates curves with automorphism group of size 54. And then beyond the isolated curves with large automorphism group, there's also some one-dimensional families of curves with large automorphism groups. And I didn't show it on the slide, but it turns out none of those are general. They all have some gonality. Okay, so in Mukai's model, we want to avoid hyperelliptic, trigonal, and tetragonal curves. And so we've got really sort of 2 examples that are in the running for us. And so the first one I'm going to study is the Fricke-MacBeth curve. So this is the genus 7 smooth curve with the largest automorphism group. It has order 504. It's isomorphic to PSL28. That's as large as an automorphism group can be by Hurwitz's bound 84G-1. Fricke at the end of the 19th century was already aware of the existence of this curve. MacBeth in the 1960s actually wrote polynomial generators for the ideal as well as matrix generators for the automorphism group acting on the ideal. And here are his generators. And you can see it's defined, or MacBeth's equations are defined over Q adjoins zeta 7. A number of people have subsequently studied this curve. You can actually write equations for it over Q, but then the automorphisms are over Q adjoins zeta 7. So like I said, you can't do everything over Q. You need the 7th root of unity either in the equations or in the automorphisms. Okay, so I'm looking for 9 hyperplanes that give the Fricke-MacBeth curve in Mukai's model. And here's how I found them. So first, I compute the kernel of sim2i2 mapping to i4, and that gives me a quadratic form. And it's not exactly the standard quadratic form if you start with MacBeth's quadratics, but it's pretty close. It's easy to diagonalize. Next, I get the induced action of OTC on quadrics of the canonical ideal. And magically, we actually get a subgroup of SO10 in this case. That's not guaranteed. That doesn't happen for the other genus 7 curve I was looking at, the one with 54 automorphisms. So the fact that this works is great. Next, we want to embed our curve in the orthogonal Grassmannian into P15 under the spin representation. And so I should find a pair of complementary Lagrangians U0 and U infinity. And here I just want to record the choice that I make. If I start with a standard quadratic form, I'm going to choose this 5-dimensional subspace as my U0. And U infinity, I can just take the minus signs off the i's. On the other hand, many authors would rather work with a different quadratic form, this one, because then that gives you the version of SO10 where you have maximal torus given by diagonal matrices. And I'll simply say that if you start with this choice and make this choice, then when you land in the basis given by U0 and U infinity, you're actually working with this quadratic form. Or you could have just started with that quadratic form, and then the first 5 rows and last 5 rows of the identity matrix are Lagrangians for this, or sorry, quadratic form. And so you, whether you start with this or this, you can sort of land in the same place. So now that I've chosen U infinity and U0, I can compute the spin representation of my automorphism group on the set of positive spinners. In general, that would be a double cover of the group you start with. But we get lucky here, and your double cover is just OTC plus Z2. And so you can actually get a representation of your automorphism group into GL16. When you do, you find that it splits as a direct sum of 2 irreducibles. They have dimension 9 and dimension 7. And if you project to the 7-dimensional representation, that gives you Fricke-MacBeth curve. Now, incidentally, none of this is news. Mukai observed this back in 1992 in one of his earlier papers, although he didn't actually write equations for the hyperplanes for this curve at that time. All right, well, I did all of this using Macaulay 2 and Magma. I got the 9 hyperplanes. I don't have them in a very nice form. It's not an output you would want to see on the screen. I didn't put it in the slides. But once I did, I had everything I needed to compute the state polytope. And I find that indeed, the freaking MacBeth curve is T semi-stable for the maximal torus that I used. Which one did I use? So if you start with this version of the quadratic form, there you have a diagonal maximal torus. That's the maximal torus that I used. Okay, and an open question. I would love to be able to say that this is one of the examples where we can extend T semi-stability to G semi-stability, but I haven't been able to do that yet. I need more knowledge of parabolics and SO10 than I currently have, but I'm mildly hopeful. I think it might work for this particular example. Okay, on to a second example. Our previous example was a smooth curve. Let me do a singular one. So let's consider the genus 7 curve with 7 cusps arranged at the 7th roots of unity in the complex plane. Then you'll get an automorphism group that's the dihedral group of order 14. You can obtain equations for this curve, and if starting from parameterization of this curve by taking a hyperplane section of the tangent developable of a rational normal curve. This is a very beautiful picture, which was used in a spectacular way by Proto, Farkas, Papadima, Raiko, and Wyman recently to give another proof of the generic Green's conjecture / Poisson's theorem. But again, just really beautiful geometry. I get the equations, I compute the quadratic form, I can diagonalize it. I use the same U0 and U infinity that I used before. This time around, I don't think the dihedral group is enough to just pin down the hyperplanes I'm looking for using representation theory. So I took a different strategy. I just produced a bunch of smooth points on my curve C, which was easy to do because I had a parameterization. And so I just constructed points on my curve. I compute the spinors of those points and the hyperplanes that are orthogonal to those spinors. And so I get my 9 hyperplanes that way. And once again, the output is nothing that you would want to see on the screen, but I went on to compute the state polytope, and it shows that this curve is also T semi-stable for the maximal torus T that I described earlier. So those are my positive results so far. Let me just mention a little bit more about what I've learned along the way. So in Mukai's model, he says that you should avoid the tetragonal curves. Well, what goes wrong? What if you try to copy his construction on a tetragonal curve? Well, I tried one, and what I found is that this kernel was not one-dimensional, it was three-dimensional. So first there's the problem of uniqueness. Which quadratic form do you plan to use? And moreover, every quadratic form in the space was degenerate. Okay, so there's several reasons that Mukai's construction won't work on a tetragonal curve. Another example that I wanted to study is called the balanced ribbon. And a good question is, will it appear in Mukai's model? All right, so what is it? It's a non-reduced dimension 1 scheme. It's supported on P1. And it has a fairly large automorphism group. Here I've just defined this example by its equations, but if you study this closely, you'll see that there's a GM acting with these weights, and there's also an involution that just flips variables in this way. The balanced ribbon has the Betti table of a general genus 7 curve. The kernel from sim2 to I2 to I4 is one-dimensional, and it's generated by a full-rank quadratic. So that's all very promising. Now, you can't construct points on this curve and then embed them in the orthogonal Grassmannian in the way that Mukai would for a smooth point on a smooth curve, because this curve is generically non-reduced. There's no non-singular points. As a result, these spaces WP perp, they're still isotropic, but they only have dimension 4, not dimension 5. And I pushed a little bit further. I thought, aha, well, if this only has dimension 4, maybe we could add a common isotropic vector to each of these 4-dimensional spaces to get a Lagrangian. Well, that won't work. These 4-dimensional spaces already have pairwise dimension 1 intersections as p varies. And so you can't add a common isotropic vector to these 4-dimensional spaces. You would need to somehow assign an extra 1 dimension to each of these spaces in a way that none of them intersect. That could happen, but if this actually all works out, I think that would be really interesting. Now, at first, I didn't think that the approach using representation theory of the automorphism group would get very far, but I actually tried it over the weekend, and I got a lot further than I expected to. I was able to pin down 5 of the 9 hyperplanes this way. So I still haven't finished this example, but I actually got further than I expected to. And so let me just briefly mention a third strategy for finding hyperplanes that give specific curves in Mukai's model. And so this is now leading us into a discussion of future work. My first observation is that when we're talking about ideals in 7 variables generated by 10 quadrics, there's sort of a canonical form that you can use to write any ideal in. So you just need to fix an ordering of the degree 2 monomials. And then whenever you have 10 quadrics, you can enter them as the rows in a 10 by 28 matrix and echelonize. And that gives you sort of a unique representation of every ideal that's generated this way. Now, on the flip side, you could start with Mukai's equations for the orthogonal Grassmannian. You could fix any 9 by 9 minor, and you could invert it, and that'll leave you 7 unknown coefficients in each row. So you've got 63 variables. You can substitute those into Mukai's equation and echelonize. All right, if you actually start with a full 63 variables, that sounds hopeless because your equations have either degree 1 or 2. You've got 10 by 10, 9 by 9 determinant. No, sorry, 10 by 10 determinant. That sounds horrible. But if you have any tricks to cut down on the number of unknown coefficients, there's a chance that you might make a variation of this procedure work. And this is my last slide of the talk, and I'll simply mention one other trick that we want to try, which is to go back to invariant theory rather than geometric invariant theory. Now, in general, for instance, when we were working with Gieserker's constructions of moduli spaces, we were in very, very high dimensional Grassmannians. But with Mukai's model, we're working in GR916. Could we produce and evaluate any SO10 or SL16 invariant polynomials on wedge 9 of C16? If we can, and if such a polynomial doesn't vanish at a point that we're interested in, that would give us G semi-stability. And I haven't pursued this in detail yet, but I'm mildly hopeful that it may work. Because like I said, in contrast with Gieseker's constructions, the dimensions of the Grassmannians involved in Mukais constructions are much smaller. All right, that is the end of my talk. Thank you very much.
Okay, thank you, Dave. Let's everyone applaud with audio or not. Are there any questions for Dave at this point? Okay, no questions? Let's see, I'm afraid I had to switch accounts here, but let me see if I can be heard. Dave, can you hear me?
Yes, I can hear you, Chuck.
Okay, it's your volume, I can't hear. Okay, now can you hear me?
Yes, yes.
Oh, very good. So I have a very silly question. So in the second example, the one towards the end, you had 3 approaches. Okay, and you said you needed 9 hyperplanes, was it? Or 9?
Yes, yes.
Okay, and you got 4 by the first approach and 5 by the second? Did you get lucky?
No, you're saying with the balance ribbon,
right.
I'll have to get my numbering right. My first approach gave me 5 hyperplanes. My second approach gives me none. Yeah, so I've got 5, but I can, sort of do this echelonization thing to try to get the remaining 4, and that's future work. And like I said, we may find it, or we might find, that there's no set of 9 hyperplanes that would give the balanced ribbon in Mukai's model, and that it's replaced by something else in the GIT quotient. So I'm not sure which of those outcomes we're going to lead to yet. I will say I was able to produce 9 hyperplanes that gave me an ideal that had the right symmetry, the same as the balanced ribbon. And I even had the right sort of number of binomials and trinomials. So I got really close, but I didn't get the balanced ribbon. And so I'm trying to work out, is it because I made a mistake, which is still pretty likely because this is a relatively recent calculation that I haven't checked very carefully yet. Or is it because you're not supposed to get the balanced ribbon, and what I sort of got was, a proof by contradiction that when you set everything up the way you would need to get the balanced ribbon, you in fact get something else. So hopefully within a few weeks, I'll know which of those 2 cases we're in. Excellent, excellent. And then this was a computation from last weekend, you said. So. Yes, I actually, when I first studied the balanced ribbon, I didn't even try the first strategy at first. I just didn't think that the automorphism group would give you enough to pin down those hyperplanes. And then as I was writing the talk, I realized, okay, I should really try and see how far you get. And the answer is further than I thought. So. Excellent. Okay, well, let's thank Dave again. And thanks to all of you.